Welcome to academic research. In today's video, I will start the modeling of mechanical translational system. So let us start the modeling of mechanical translational system. Mechanical translational system. So translational system means the motion in a straight line. For example, of some translational system or car, bike which moves in a straight line. So translational means motion in a straight line. It means the object which moves in a straight line, that is called translational system. For example, the simple example in our day-to-day life we are using, that is bike, then car. So generally this mechanical translational system having three basic elements. This system having three basic elements, that is, one is mass, second, that is your spring, and the third element is damper or dashpot. So generally in this system, what happens, the weight of the system, the point 1, the weight of the system, the weight of the system is represented by mass, which is concentrated at the center point. That is called ideal mass. Means the mass which is concentrated exactly at the center and it is not affected by other elements. It is called ideal mass. So here we have to consider the ideal mass to make the model linear. So next important point, the elastic deformation. The elastic deformation represented represented by a spring. So here spring means we have to consider that is your uh, linear spring or ideal spring. It means the deformation takes place by the spring is uh, elastic deformation. It means after removal of force, the spring should come to its original position. Therefore, it is called elastic deformation. That is another way we can say that is your ideal spring, or it is called linear spring. To make the model linear, we have to consider the spring is ideal or linear spring. The next important point we have to note down the friction of the body. The friction of the body is represented by a damper or dashpot. So already we know about the damper or dashpot. Means inside a cylinder a piston is there which can move freely in any type of medium, that is either gaseous medium or liquid medium. So that is called damper or dashpot. In this case also we have neglected the Coulomb friction and static friction due to nonlinear nature. We have considered the viscous friction only because viscous friction is most effective in this case. Therefore, to make the model linear, we have considered here only viscous friction. The Coulomb friction and static friction or stiction, that is neglected due to nonlinear nature. Therefore, we can make the block diagram of the mass spring damper system. So the block diagram of a simple mass spring damper system, that is your mechanical translational system. So this is the block diagram. This is the mass M, and this is the damper which having the coefficient of viscous friction B, and this is the spring, that is which having spring constant or stiffness of the spring is represented by K, and this is the applied force F of T, and due to applied force this is the displacement X of T. Therefore, in this type of control system, here we have applied the force that is input force is Ft and the output force, that is output of the system, is displacement, that is x of t. And this is the simple block diagram of a mass spring and damper system. For example, car or bike. So let us discuss first one by one, that is mass, spring and damper. Then finally we can connect all the blocks to form the mass, spring, damper system and derive the differential equation individually for mass, spring, damper system. So let us first draw the free body diagram of mass. First we will discuss mass. So let us draw in this side. This is the mass system and this is the applied force F of t and this is the displacement x of t and this is the reaction force Fm of t. So here when the force is applied to mass produces an acceleration, so a reaction force, that is Fmt, is equal to product of mass and acceleration produces in opposite direction. So this is the reaction force which is exactly equal to the applied force F of t, which is equal to the product of mass and acceleration according to Newton's law. Therefore, here the force due to mass is equal to mass into acceleration, which is equal to mass into dv of t, that is derivative of velocity, which is equal to mass into d square x of t by dt square. So this is the mathematical equation for mass, and let us derive the mathematical equation for the spring. So this is the spring force. This is the F of t, and this is the displacement x of t, and the reaction force F of k of t, the spring stiffness here, K. So, when a force is applied to spring, the reaction force Fk in each end of spring is same and equal to product of stiffness, that is spring stiffness K, and the amount of deformation xt. Therefore, Fkt is equal to K into x of t. So, this is the mathematical equation for spring. So, let us discuss the mathematical equation for damper. So, for damper or dashpot, so here we have given one applied force, that is input force is F of t, and due to that one displacement occurs, that is x of t. Immediately one reaction force is developed, that is opposite direction to applied force, that is FBT. Therefore, FBT is directly proportional to velocity of this piston, and is equal to velocity, that is product of the viscous coefficient B and velocity of the piston, that is FB of t is equal to B into dVt by dt, or which is equal to Fb of t is equal to B into dx of t by dt, because the derivative of displacement is equal to velocity, that is velocity is equal to dx of t by dt. This is the derivative of displacement. Therefore, FBT is equal to B dxt by dt. Therefore, if we will combine all the three elements, this forms the spring mass system. The simple example is, let us take one car. So this is the mass of car, and this is the spring, and this is the damper, and this is the wheel of the car, that is car wheel. It means the car is suspended. The car is suspended by the wheel. So here the mass of the car or weight of the car is called mass, and that is the wheel having the spring and damping system. So the the car is the best example of mechanical translational system. So another example is the bike, that is weight of the bike is called mass, and the wheel of the bike is suspended by the help of spring and damping system, that is For example, that is your shock absorber of the bike. Therefore, now we will combine these three equations to derive the single differential equation for spring mass damper system. So let us combine the three equations, that is f of t is equal to fm of t plus fb of t and plus fk of t, or f of t is equal to m d square x of t by dt square plus b dxt by dt plus kx of t. Therefore, this is a linear differential equation because this differential equation is in descending in order, and therefore we can solve this equation easily by transfer function method. Now we can take this we can take the Laplace transform of this equation, and we can find out what is the transfer function. Then we can analyze the system. So that I will do in the next class, in my next lecture. Thank you very much.